A street light is mounted at the top of a 12-foot pole. A woman 5 feet tall walks away from the pole with a speed of 4 feet per second along a straight path. How fast is the tip of her shadow moving when she is 30 feet from the pole? So the first thing we need is a good sketch of the situation. So we've got a pole here. It's 12 feet tall. That is not changing. So there's the light. We have a woman. She is 5 feet tall. That is not changing. The light and woman make a shadow here. That's our shadow. That is changing as she moves away. Then the shadow is getting bigger. Also, um, the shadow is moving as she moves away from the post. So we have to decide what we want to call x in this problem. If we call the distance from the woman to the pole as x, then dx dt is the speed of the woman. That's not what we want. The question is, how fast is the tip of the shadow moving? If we call x the length of the shadow, then dx dt is just how quickly the shadow is growing. That's not what we want either. If we call the total distance from here to the end of the shadow, from the post to the tip of the shadow, now our dx dt is how fast is the tip of the shadow moving. Because the tip of the shadow moving is a combination of the shadow, the whole shadow moving, in this case to the right on the page, and the shadow growing. But we do need some kind of variable for the distance that the woman is from the pole. So I'm gonna call that y, because I know that dy dt is equal to 4 feet per second. So now I can write the length of the shadow in terms of x and y. So the length of the shadow is x minus y. So let's state the problem. The question is, what is dx dt when, in this problem, the when is when y is 30 feet, because y is the distance the woman is from the pole. For this problem, we can take a look at similar triangles. So here's the big triangle of the pole and the total distance. Here's a smaller triangle of the woman and the shadow. What I want is I want an equation that has x's and y's in it so that I can take a derivative and get dx dt's and dy dt's. That will allow me to solve for dx dt, because that's the goal. What is dx dt? So I'll use these similar triangles and say 5 is to 12, like x minus y is to x. And then I'll clear out the fractions and say 5x is 12x minus 12y. And then combine some like terms and get 12y is equal to 7x. And now I can take the derivative. Derivative of the left-hand side is 12 dy dt. Derivative of the right-hand side is 7 dx dt. I know from my picture here that dy dt is 4 feet per second. Also, we have to pay attention to the sign of our rates. Our sign is positive 4 feet per second because y is growing. It doesn't matter the orientation that we write this. Since y is growing, the rate is positive. If this woman had been going towards the light, then y would be still a positive number, but the dy dt would be a negative number since y would be getting smaller. So we've got 12 times 4 feet per second is equal to 7. I'm going to divide both sides by 7. 12 divided by 7 times 4 feet per second is equal to dx dt. Notice in this problem, we didn't have any y's left to substitute back into the problem, and that's okay. What that means is this shadow is moving at this rate, irrespective of how far away from the pole that she is. And so my final answer is going to be 48/7 feet per second. The key to related rates problem is get a good picture so that you can get an equation with the things that you have and the things that you need in it in order to take the derivative and then solve for what you're looking for.